Okay, thanks for coming to my talk. I know it's after lunch, so some of you may be a little bit sleepy. So I'll do my best to keep you entertained.
Wake up.
Although there will be no jokes because I'm not good at jokes. But hopefully my presentation will be at least informative for you. Okay, the subject of the presentation is large-scale distributed processing in Google Cloud. But the principles in this presentation can apply to any distributed processing, not only in Google Cloud, but also in other cloud providers. Okay, so very short about me. So I'm a principal big data engineer at Sabre. And Sabre is a technology company building software for the travel industry. I've been working in big data for the last 9 years, and in the old on-premise times when we had servers in our data centers, we were doing big data, and I was responsible for designing that, for developing big data projects on-premise. But in the last 2 years, we moved to GCP, and I'm doing the big data native solutions, implementation, development, and I was responsible the last 2 years for migration from on-premise to the cloud. This year, I'm responsible for optimizing the jobs and for cost reduction for all the jobs in our data and analytics organization in Sabre. I'm writing my technical blog on, you can see the links there. You can see my GitHub repository with the code that will be present here, and you can catch me on Twitter as well. So the agenda, there will be very two quick introduction to big data, and there will be 6 code examples, plus all the metrics, so you can help me optimize the code. And if time permits, at the end of the presentation, I will show the architecture of our most, one of the biggest projects that we did on GCP, our core products. I will show the architecture, and we'll summary the lesson learned and some other bonuses as well. Okay, let me start with a quiz, just I promised to wake you up a little bit. Who worked already with big data a little bit, or know what it is? Okay, 40%, okay. So in a nutshell, big data is about high volume of the messages. Sometimes we receive messages more than a couple of thousand of small messages per second. Sometimes we receive like 220, 250 of really fat, big XMLs compressed. We receive data in different formats like JSON, XML, Edifact, the CSV. We do some data massaging, data verification, cleaning the data, so we make sure that they will give us some business value for further analysis for the data scientists. So when you think of distributed processing in big data world, the common term that is used is extract, transform, load, so ETL jobs. And in the past, we use on-premise, we used Hadoop MapReduce jobs. You can still run MapReduce on Dataproc, but it's kind of depreciated. I've got some experience in writing multiple jobs in Spark. You can run them also on GCP, on Dataproc, an option standard, and in serverless as well. But in this talk, I will be using Apache Beam framework run on Google Dataflow. But again, I will be showing the concept and principles, and these are not really only specific to Dataflow or Apache Beam. The last overview before we jump into the examples is the overview of Apache Beam. because I will be showing you the code, so it's good to understand high level what this consists of. So Apache Beam is the unified programming model for a batch and stream processing of data. And what is really a batch job is a batch job if you know all the data in advance what you'll be processing, then you exactly can calculate the progress of your processing, so you know when your job completes. But for the streaming case where your source is unbounded, you have a continuous flow of elements, of the events that you want to process. And you can write the same pipeline in Apache Beam, and you just set if it's streaming, yes or no, true or false, or even use the unbounded source, and it will be set by default. You can run your code once, and you can use multiple runners. So I've been doing, for local development, I've been doing using the direct runner. On Dataflow, we use Dataflow runner. I also run the code using Spring runner. I know some of you are trying Flink, so there is also a Flink runner. So the same code provides the abstraction, and you can plug in via parameter which runner you want to execute. And you can use several languages to write your code. On the slides, I'll be presenting the Java version. I also written the Python, Go, and SQL is also available. So the Beam SDK provides many connectors. So from reading from the source, like Kafka connector, PubSub connector, and many more. And also, we eventually write the data after transformation to the sink. And there are many sinks for that available, like for BigQuery that we use, GCS. So this is really the high level. So let's start with the example and the code, because there will be lots of code and hopefully some interaction as well. So what you see on the screen is Apache Beam pipeline that's run on Dataflow. And I was trying to organize the code into 5 blocks. So if you look into the first block on the top, you can see how we define the pipeline parameters. So we define some custom arguments like sequence limit, number of shards, and then we define some runner-specific parameters like what kind of runner we want to execute upon the pipeline, and what will be the machine that will be used for running the job. So we can pass multiple parameters declaratively. We can even parameterize that and pass different on different environments. So that was the first block. The second block is I define a source, which is like the first rectangle that you can see on the top. And in our case, I'm showing you a source that is able to produce a sequence of elements from 0 up to the limit that I pass in configuration, like 6 million here. And this source is able to produce these long elements in parallel. So if we add 5 machines, all these 5 machines will be receiving the data in parallel. And it's really fast. You can configure the speed of sending the elements and many other options that I will present later. At the point here, we have a source that mimics like the processing if we receive the data from PubSub or from Kafka. Then we've got the middle block, which is, we call it a user code, where you can see map elements. And the point of this block is really to generate 1 kilobyte payload. So this time I'm randomizing the payload to keep our workers busy. And in the block before the last, there is a sink which is a text IO write, where I define where should I write to. So it could be S3, a bucket, it could be a GCS bucket, and I define number of shards. And up till now, if you execute that, nothing happens because you need to execute pipeline.run. So you need to have, like, you know, in starting from Java 8, you got these streams, and eventually on the streams you need to call a terminating operation, which is like .collect and pass the collectors for. In Spark, you can build a data set. Eventually, you need to, for example, execute show or save, so the pipeline code gets triggered. And so this will be our starting point. So if we run that pipeline, the Apache data flow provides built-in lots of metrics. And I will use these metrics. I just copied the most significant ones for our talk. So we make a pipeline optimization. So can we increase the throughput? So what is the throughput here? The throughput is, for this pipeline that I just defined, it's up to 6,000 of elements per second. And what is the CPU utilization? It's 100%. Is it good? Some people say, yes, we are using the full capacity of the workers. All the threads are busy. We are running full speed. So probably we are done. Looking into memory, the memory is not used so much. We use like 8 gigs out of available 63 gigs. So I don't expect any GC happening here. So that would increase the CPU. And really the question is, can we increase the throughput? What can we do with that? Let's get back to the code. Let's say that the purpose of this code is to test how fast we can write the data to GCS in that case. So it doesn't really matter what we put inside. Let's kind of modify this code so we will be still sending 1 kilobyte messages, but let's try to increase the throughput. So any ideas? What can we do to modify that code to increase the throughput? Okay. Okay. If you change the sequence limit, that's a bad job. So what it means in the sequence limit is that you want to store eventually on GCS 8 million of 1 kilobyte of messages. So if you change the limit to not 8 million, but maybe 100 million, probably the throughput will be the same, but the pipeline will execute longer. Okay, we will get to sharding. That's one thing, good. So it will be a very obvious, simple change here, so don't be surprised. But before getting there, let me give you a little bit more hint. So if you look into the built-in data flow metrics, we can identify which step is taking the most time. And data flow provides the breakdown what's really happening internally, and that execution of the job is divided in many steps. And the name of the step is called stages, and we've got like stages F21 starting and then ending with F, I believe, 18 or 17. So what's really happening here is that generate sequence, map elements, and even rewindow into global. That's all happening, even though these are 3 different stages of the pipeline execution. The data flow can see there is no group by operation in between. So there is no really checkpointing needed. So what you can imagine is that generate sequence, map elements, and this rewindow into global, it will be executed the execution will be fused. So imagine like there could be one thread that would generate the sequence and serialize the data, then deserialize and do the map elements processing, and serialize again and rewindow into global. But that would be slow because of the serialization here. But nothing really happens in between these 3 steps. So data flow fuses them, and Java thread executes all these 3 stages like one after another. But what is important here in map elements, you can see the wall time, and the wall time is really how much of the processing time cumulated. So total of the processing time is being used for executing the map elements. It's a sum of CPUs from all the threads that were busy doing that map elements, and that's 5 hours. And that phase, F22, takes the most of the time. It's not the writing. That writing would be F20. Writing is 25 seconds. But the elapsed time of the phase F21, I'm looking right now on your right, the diagram. So this phase takes the most of CPU and takes the most of elapsed time. So after a hint, let's get back. Map elements. That is what the metrics are recommending. So what would be your very naive implementation to make this step faster? Awesome. Okay, let's do that. That would be a very, very simple change. Use the sequence and the static payload. Still, it's 1 kilobyte of message. So if we replace that, if we remove the UID generation, if we remove the Apache Commons generate random ASCII, I'm still generating 1 kilobyte of messages. But the thing is, the whole concept here, if we optimize the CPU time for the custom code that we write, maybe we can improve the throughput of overall the pipeline. And try to guess what would be the throughput of the pipeline before it was 6. Now can be? Okay, close. 47K. Just with the simple of that. The throughput has increased from K to 47K. Interesting. CPU utilization was 100, and now it's only 15. And still, the memory is low, so there is no really GC happening here. So it's worth to optimize your user code to remove, to make sure that the overall pipeline execution will be faster. What else happened in the same metrics? The map elements wall time got reduced from 5 hours to 4 seconds. The pipeline elapsed time execution, so how long all the pipeline was running after it finished, it got reduced by 5 times. And the elapsed time of that specific stage that it was taking the longest got reduced from 22 minutes to 2 minutes. Okay, did we save some money? Oh yes, we did. From 46 cents to 8 cents. That's a built-in dashboard for Google data flow that provides us some estimated cost. It doesn't include any discounts or adjustments. It's a rough estimate. How much of the resources were used and for how long. And if you look into these small boxes, you can see really how much we saved on each of the components that we are paying for. Biggest save was on virtual cores, on vCPU. Okay, so the lesson learned is try to optimize the user code as much as possible. So if you look now, you can see the parallel is green because it's highly optimized. The sequence is SDK built-in solution, so it's really fast. We have CPU optimized the user code. Okay, can we go faster? Can we pay less? Any other guesses? There was one guess about shards, and you were right. If we get back to the pipeline, you can see here that I'm specifying the number of shards equals 16 in the pipeline execution. I'm running on the 16 cores E2 standard 16 machine, a single machine. And I'm now playing with how many shards can we use to optimize the pipeline. And these are the results of the optimization. Obviously, having too little shards can increase the can keep the group into shard fate small, but really the step of writing the temporary files to GCS will take long. And we've got 16 cores. We have 16 cores, and only writing to two shards is not a good idea because the overall pipeline execution will be 20 minutes. So I did the multiplication of number of cores, and you can see that with exactly the number of cores and shards, we've got pipeline execution time dropped by 2 to 9 minutes. If 32 shards, so 2 times more shards than cores, there was a little bit of a gain, like 26 seconds, and even running the 64 shards, another 5 seconds difference. So we need to find the best number of shards, because going too high is not also too good, because stage F21, which is about grouping, so preparing the shards, will take longer and longer if we use more shards. And what Apache Beam does underneath, it writes these temporary data to temporary files into the bucket. This is an example of a shard 9. And eventually it will move the temporary data to the output CSV that we have a control over how to name it. And the reason why I made this output file green is that if you ever will be writing to GCS and you want to write with high speed, really small files, it's better to prefix the file name with some hash that evenly distributes the load across GCS servers. And so it could be just as simple as if you have your final file name, you can calculate MD5 out of that file name and take first 6 or 8 characters and prepend the file name. That will increase the write and read throughput from GCS bucket. Okay, can we go faster? What else can we do? We improve the number of shards. I set them here 128, but the results were close to 64. Can we go faster? Any other guesses? If by faster machine, that's true, and this will be after that. But One disclaimer to what you said. If we are running machine E2 standard 16, and if we choose E2 standard 32, that means we will choose the same machine family, but with the twice number of virtual cores, the cost of that machine with the twice number of cores will be more or less twice as much as with 16 cores. And you know, if you look into pipeline execution, the faster machine will accomplish the same work 2 times faster. So you pay 2 times more, but for the 2 times shorter period. If you multiply them by together, you will end up more or less with 1 to 3% of a cost difference. But it will be the same if you use the same machine type, the same machine family for the batch job. Okay, but there is something in machine types. Let's do it in a second after that. Any more suggestions? Okay, that may be obvious, but it matters if you write to the bucket, which is either regional or multi-regional. And especially if you're writing files which are lots of small files, then the difference in writing can be around 30%. So if you're building a pipeline that writes some data temporarily to GCS, and there is a second pipeline that reads from that GCS and writes to BigQuery, which is our case. I will show you the architecture at the end of the talk. You can actually, and data flow runs only in a single region. And these are the same regions, and usually these are, there is no point in using multi-region bucket that internally has the replication cost. So specify in the pipeline parameters the temp directory in the output directory, the bucket that it's regional. And what's the savings here? Elapsed time from 12 minutes to 9. Cost not so much great, but in essence, the smaller files you get, the bigger cost difference there will be. And if possible, try to prefix the file with some hash for faster write. Okay. A different use case. We are getting closer what we have in our final production project. We are not processing the college data. We are in the travel industry. But this is the example from the D-Zone about VTD XML parser. This is the parser that we use for parsing XMLs. XMLs that we receive are really big XMLs with like 7 level of nesting, that you have like a record. That record has arrays inside. Inside arrays, you've got another records. And these records in the array point to another part of the XML. So there is lots of XML processing. And we came up with declarative XML parsing using this VTD parser. So we specify, okay, I want to have a map at the end of a processing with the key that will contain a college ID. So I say, at ID, because that's the ID at the root of the element. But if you want to know what's the department name for the first staff department, just use the first declarative approach. And if you need some custom processing of XML, which will be the case for our further journey, we want to sum the basic salary across all the departments. We have admin department, we have HR department. So if it was just a simple of that XML, the staff basic salary sum would be 20,000 plus 25,000, 45,000. This is the value we would expect from parsing that single XML, and we will be processing lots of these XMLs. So, and this VTD XML parser is a really great tool if you need to process even huge XML. It has a huge version of VTD parser, and in other projects, I was doing tests for XMLs that were 23 GB, and even you can go further with really high speed. That processing is CPU bound. So really the CPU matters here. Okay, so the example right now of a different pipeline that is processing that XML that we've seen here, right? So what's really happening here? Again, my favorite generate sequence, because that keeps me the pipeline cost low for this presentation. So I'm taking the payload, the XML payload that I've showed you from college. And what I'm doing here, I'm putting this payload 1,000 times into the, I'm concatenating this payload 1,000 times and convert it to bytes. And this FAT, and at the end of the day, I'm gzipping that. So I have a gzip that have this 1,000 of XML inside. And I'm trying to process that XML to really have a sum of all basic salaries across all XMLs, across all the departments. That's my goal. Okay, so I hope you understand the goal. Again, this is still the, and this is still the batch job. So we know in advance that we will be processing with the sequence limit 5,000. So bottom line is that we need to process 5 million of XMLs, and we want to get the sum of salaries. So what are the results? Let me show you the pipeline first. So these are all the building blocks. What can we say about that pipeline if you see that on the screen, especially the built-in dashboards? We have a straggler. Straggler are work items that preventing the work from paralyzing. Okay, and we've got a low CPU usage. And I told you just before that this XML processing is really CPU intensive. So were I lying? Is it not really true? And can we go faster? What can I do? Tell me. Okay, so as you know, gzip compression is really effective. Gzip compression, so it really likes it can really compress huge data, and it's really good to use gzips, for example, to send it to PubSub, because you also pay for the storage, and then later you can decompress it. Don't send, especially in the big data area, too much of the data. Uncompressed, because you will get a huge bill for PubSub. But it's good to compress it. But let's see. Okay. But the problem here is that gzip is not splittable. So imagine you receive that huge fat gzip with 1,000 of XMLs, and you've got your pipeline, your worker with Java threads running. One worker, so one thread gets the fat XMLs and try to decompress it, and it's really slow because it seems like it's a single threaded, even though we have like 1,000 of XMLs. So what we can do actually here, it's not the change in the code that we will do, but if we have a possibility to talk to the source of who is sending us the XMLs, it would be better if the same amount of data is not packed into batches of one gzip files, but to have a one gzip for one single XML. So single XML. And let's try to guess what will be the throughput. The output throughput is 4.2 elements per second. So what would be the throughput if we don't send like a compact fat XMLs, but send gzips individually for small files? Try to guess. 100, okay. Okay, 24K. That was the throughput. So the throughput increased, I don't know, by 5 times. Just only if we have the same data differently packaged. So you can see the modified version of the same code, the modified version of the same flow, but this time we are accepting a single payload gzip with, instead of 5,000 of elements in this 5,000 of elements in a sequence, but 5 million. And the same logic applies, we'll get the same results. And estimated cost got reduced by 4 times. Can we go faster? Machine type. There is a Google on a web page. They maintain for their machine families. They maintain so-called core scores, and by going into that web page, you can find the CPU scorecard for each of the family. And by doing that, I was able to find my old machine E2 standard 16 and compare it with other machines. There was E2 high CPU 16 machine, which had a much better scorecard. Like, if I remember correctly, the old one was 200, the high CPU was 260. So we could change this to the high CPU, and there would be, because it's a really CPU-bound processing, there will be already a gain at about 20-30% of the more effective processing, so shorter execution of the pipeline, and the cost drop by 30%. And imagine your pipeline cost millions. 30%, that's a lot. I wish I had that in my pocket. But I didn't get it to my pocket. And I went for even different machine, not a high CPU, but I found out there is a great performance per dollar tau machine, T2D machine, and which offers actually 55% higher, 52% higher performance compared to the like E2 standard machines. And actually they were right. If I use T2D standard 4 machine, my cost went down from 4 to 2 by 20%. Imagine the scale of millions of dollars. And there were no stragglers. We were able to process fast. The stragglers were gone when we parallelized the messages, not a fat jar, not the fat gzip, but the individual gzips for single messages. I believe that was number 5, and the last optimization that we can do for the pipeline, that's still the same as XMLs, but this time someone is interested. Let's imagine that we've got this continuous flow of incoming data, incoming XMLs to our system, and somebody is interested in knowing the sum of salaries, maybe a little bit artificial example, sum of salaries every 10 seconds. So the elements that are arriving will be grouped based on the time when they were generated by the source. So if you look into the source, I'm using the generate sequence, and when the element is generated, I'll assign the instant now. So each element will have the timestamp when it was generated. So I'm looking into the timestamps of these events and group them into 10 seconds windows. And across these elements, I'm calculating the sum of salaries, but this time per country. So I've chosen 3 countries or 3 places where I've been to: US, Poland, and Malta, for some reason. What can go wrong? What can go wrong with that pipeline or with that data? Give some time for thinking. No pressure, guys. So in reality, the country code or any can go from the payload that we receive from PubSub or from Kafka. So we don't really need to parse the payload to get this attribute. Usually it's being sent to us along with the payload. Okay. Any more guesses? Okay. Let me give you a clue. The pipeline has changed only in the last line. So the problem with that pipeline or the job execution is so-called hotkey and data distribution queue. So this is the common problem in the big data world, especially for the streaming jobs, is that when your data is not evenly distributed. And so in here, the US as a big country is like 7 times in the list, Poland is twice, and Malta is only once. And why is it a big problem? Because if you look into, I'm now running 3 workers, so 3 nodes. You can see in the middle of your screen, the CPU usage of one worker that it's highlighted, it's 62%. The second worker is only 15, and the last one is 5. What it really means is that most of the work is done on the first worker, and the other 2 are almost doing nothing, and we pay for them. And actually, the last 2 are waiting for the first one to complete. So what's the throughput? Around 10K of the pipeline. And what's data freshness? So for the streaming jobs, we define a metric that is called data freshness. So we know the time when the event was generated in a source and when it was ultimately processed by the pipeline. And if we see here 6 minutes, so it means it usually takes 6 minutes for the element to be produced and the final aggregation is output. Let's get back to that pipeline for a second. So let me explain what this pipeline really does as an example, as you know already the hotkey issue. So there is some coloring that can help us understand that. The trick is in the group by key. What really happens in big data processing and the group by key is that data is, when the group by key is called, data is stored on the disk or sent to the Google shuffle engine. And then after storing, the elements with the same key are transferred to the same machine. So if you look into the example which is in the comments, you can see key value US 11, key value Poland. Maybe I can use the mouse here to show you. So we've got 3 key values of like a Scala tuple. key value for US, 2 of them, which is, I thought I was, so you can see here and here, and they are, and we've got one for Poland and one for Malta. So what really happens after group by key create is that US are executed on, let's say, black worker. What color doesn't really matter, but all the US elements go to the same worker. It cannot be that 2 workers have US elements. And the Poland, so the key is PL, and the Malta, it can be on the same worker as US, but it can be on a different one, right? So the more US elements, the busier will be the one worker, US, because all the elements with the same key will end up on the same node. So what's the solution to resolve that hotkey and speed up the pipeline? Okay, let me show you here. This hotkey, one more comment here about this hotkey. If you look into the backlog bytes, you can see this growing, ever-growing blue line. That means the pipeline is not able to catch up processing the data and the backlog increases. So that's another metric that we can use. We can see the hotkey also on the other dashboards and showing possible stuckness. I use the counters to show that in yellow, the machine name is processing US traffic, and it has processed 68 millions of elements only on that single machine, and also that single machine, the same machine, was processing all the Poland traffic. So that the second machine was processing the Malta, and the third machine was not processing any data. But you really see that this yellow worker is really overloaded. So how to fix it? Very good. Very good. Exactly. So I'm getting the same results again, but I'm adding 2 or 3 steps. One in the middle, which I will be adding as key suffix, and you can see here that the suffix is the key is no longer US, but now it's US/0. And it can be also US/10, US/20. So I'm doing some intermediate aggregation on the subkeys. And I can evenly distribute exactly the work across all the workers. And then eventually this temporary results, I can sum them up and still get the same output, still value. So you can see that I'm still using the group by key, but the key in that case is more distributed. So we will be getting, like in my case, 61 keys instead of 3 keys. And what was the throughput in our scenario? 10 kilobytes. Now, what is the throughput? 30 kilobytes, 3 times faster. The latency, so the data freshness was like 6 minutes. Now it's only between 20 seconds and 30 seconds. And the CPU usage, all CPUs are burning. We are not wasting our money, and the backlog is not increasing, but even decreasing. So the summary of the lessons learned, I will just recap the first 5, and we will see how many questions we have. Then I can maybe move forward with the last slide, but let me recap what I said. Use metrics and execution details and dashboards to tune the performance. Parallelize the job execution as soon as possible, so receive like individual messages. Google is really good in processing fast, small messages. Don't put too many payloads inside one message. The tune number of shards or use auto-sharding. Some of the SDKs allows auto-sharding, so the runner can auto-determine the sharding. use the scorecard to find the best performance machine. And actually, what's interesting, the machine that was faster and saved us huge amount of money in Sabre was not a 16-core machine, but 8-core machine that was faster, but running on a different processor than 16 cores. So this Tau machine was is really great for us, and we noticed 50% cost reduction in the pipeline execution. Check for hotkeys and data skew, and don't use logging. In big data, if you process billions of messages, you will pay a lot for the logging, and the logs get probably throttled, so you don't see them all. And one side effect of too much logging exceptions is that when you want to see what is the exception, you will see null. And I was surprised. Why is my job producing error and I see null as exception? And I learned that if this optimization from Java, that if the same error happens again and again, the GVM stop putting exception stack trace in the code. It will just put in the logs. It will just put null. So you can disable it via using a flag, but it's optimization by default they are doing. Okay, the time is up. I'll open up for questions, if there are any. And if not, I can do the bonus. I don't see any questions, so last chance for questions. Okay, there are no questions, so there will be a bonus. Be prepared in your pipeline for the slowdowns. We've seen the case that the same code running for weeks suddenly slowed down by 2-3 times. Be prepared in your pipeline design that such a temporary, hopefully temporary is short in terms of days, but temporary slowdowns will happen, and be prepared for that. So if you have SLAs on delivering the data, you will still meet them. So be prepared for that, because there will be. Even though for 10 weeks it's okay, the 11th week may go wrong. Optimize the cost by using preemptible VMs. Especially, I recommend doing that with managed services, because you don't need to take care of when your pipeline, when your machine gets taken away from you. All the managed services like Dataproc or Dataflow can handle that for you. So, for example, Dataproc is a cluster where you can run Spark, and you can set the default pool of machines and the secondary pool of machines where if there are these preemptible machines, so aka the spots, it will use them, but if they are not, it will run the normal ones. So go for Dataproc with secondary workers, or use the Dataflow with preemptible VMs, but remember that the job will not start immediately. There is no guarantee it will start immediately. It can start up till, there is a guarantee it will start in 6 hours. So for the scenario that you need to generate a report and you have a luxury of 7 hours, go for preemptible VMs, you will save the cost. And I covered the distributing of the file names. The last slide is about the architecture. So all the examples that I made up for today were based on this example for a shopping, when we processed really fat messages, and we couldn't scale above 80 TPS of these fat messages. At the very beginning, we spent months on trying to optimize different things. And eventually what we did, we created a first pipeline that will split the big messages into chunks. After reading from Kafka and putting them to PubSub. And it was really paying out. We were able to go really faster if we had small messages in the later stages of the processing, where we convert XML and store them first onto GCS with a streaming job, and then have a scheduler Cloud Composer that will read the messages, schedule the job every 30 minutes to read the files from GCS. The files had a date notion in their name, and load it into the BigQuery so the analysts can build the tables and run analytics on the top of that. And if you're interested in knowing how the architecture has evolved for shopping on our case, I had a talk on that last year on JDD conference, so you can watch it. It's available on YouTube. And I will be really happy if you provide me some feedback to my talk. Thank you, guys.